This will be a short video on stoichiometry, but these are gases that are not at STP. Okay, so reactions that are happening that are not at 0 degrees Celsius and 1 atmosphere of pressure. So here's your first reaction, hydrogen peroxide, which probably is actually a liquid, aqueous. So remember, when something is aqueous or liquid or solid, we do not put it into PV equals nRT. Okay, the ideal gas law is only for gases. Okay, so PV equals nRT is only for gases. Oxygen gas, we'll say water probably is as a gas here in this reaction. So it's telling you we have a liter of oxygen, which we know for sure is a gas, at this temperature, this pressure. Okay, so remember, a certain volume of gas at a certain temperature and a certain pressure will have a certain number of moles. Okay, and it doesn't matter what gas it is. It makes no difference if it's oxygen or helium or hydrogen, but a certain volume, temperature, and pressure will have a certain number of moles in it because there's that many molecules packed into that space at that temperature and pressure. So we're trying to finish with mass of that. So we're starting with oxygen going to this. So we still have to make sure we take into account our mole ratio when we do this stuff. So we have V, T, and P. We probably need to plug into PV equals nRT and get moles. So we're going to go PV equals nRT. Put our pressure in, 740. Remember, that needs to be an atmosphere, so 740 over 760. Volume is 1 liter. Trying to solve for moles. 0.0821 for R. Temperature, remember, 273 plus 25 would be 298 Kelvin. So we're going to take this, divided by those. So our number of moles here is 0.0398 moles. 0.0398 moles. Remember, I get people a lot of times that stop there and say, okay, well that's moles of H2O2. It's not. It was the pressure, volume, and temperature of oxygen, so it's moles of that substance. Okay, so that is moles of oxygen. So now we're starting our stoichiometry off with moles, which is nice. Once we're at moles, we can do our mole ratio, 1 to 2. For every 1 mole of oxygen, there's 2 moles of H2O2. Moles cancels, and a mole of hydrogen peroxide would be 34 grams of hydrogen peroxide. Moles cancel. So we're left with grams of hydrogen peroxide. So fairly simple. You just got to do ideal gas law in there. You get about 2.7 grams. Probably could have 3 sig figs of this, but 2.70 grams of H2O2 could be produced from that much oxygen. Okay, so that wasn't a limiting reactant problem. We're using all that oxygen, we'd use all that hydrogen peroxide. I could give you limiting reactant ones. We will do that down the road here. This one's starting with 6.2 grams of hydrogen peroxide. Wants to know how many liters of O2 at this temperature and pressure would be produced. So we're trying to solve for volume. They give us the temperature, they give us the pressure. All right. So in this case, I want to do my stoich first to get moles of O2, plug into PV equals nRT to get volume. If it was at STP, I would just use the 22.4 to get to our volume, but it's not, so we've got to use ideal gas law. So starting with 6.2 grams of hydrogen peroxide, 34 grams is a mole of hydrogen peroxide. Again, got to do our ratio, 2 to 1 for every 2 moles of hydrogen peroxide. There's 1 mole of O2. So I'm going to stop at moles. Don't want to go to grams. I can't do 1 mole is 22.4 liters because we're not at STP. So we get our moles of O2. Moles of O2 is 0.091. Up here. So there's our moles of O2. So now we have temperature, pressure, and our moles. We can solve for volume. So I'm going to go 750 over 760. That's our pressure. Trying to solve for V. Put in our moles, 0.091, 0.0821. Might be going off the screen here, I apologize. And then our temperature would be 273 plus that would be 288. Just plugging in, solving for the volume. I got a volume there of 2.18 liters of oxygen. Last one here. I'll move this up just a little bit. Last one, mass in grams of potassium chlorate, so we're using a different equation. Notice that is a solid that must be used to produce 1.5 liters of oxygen, measured at 18 degrees Celsius, and 0.95 atmospheres. So we can go, we want to get to potassium chlorate in grams. We want to finish with that. It's giving us information on oxygen. So let's do PV equals nRT first. So we got pressure is 0.95, it's already in atmospheres. Volume is 1.5 liters. Solving for moles, remember that is moles of O2. Sometimes I make a little note of that so we know what we're getting moles of. It's not going to be moles of potassium chlorate. R is 0.0821, and our temperature 273 plus 18 would be 291. Solve for moles. Our moles there is 0.059 moles of O2. Do a ratio, 3 moles of O2 to 2 moles of potassium chlorate, 3 moles of O2 to 2 moles of KClO3. If 1 in moles would be done, it wants grams, and a mole of KClO3, 122 grams. I got 4.85 grams. So not a whole lot different there from what we've done. One thing I will say, if it's a liters to liters question, so if it is, say this was a gas, if we were going from liters of this to liters of another gas, as long as they're gases, okay, I've never given you liters of something that's not a gas unless I give you a density. But if it was liters to liters, remember you can just do the ratio, even if they're not at STP. As long as they're at the same temperature and pressure, you don't have to do ideal gas law twice. Okay? If this was at a different temperature and pressure than this one, I'd have to do ideal gas law to get moles of this, do my mole ratio, then do ideal gas law over here to get the volume of it. So we'll do something like that. I did put one of those on here, but we'll do some of those down the road here.